So now we're going to have a look at comparing population proportions. So this is only on the new A-level statistics syllabus. So we use this test where we have two populations to see if two populations have the same proportion of members having the same attributes. It can be used when the samples must be large enough so that the normal approximation are appropriate. So that means that we need both NP, and this here should actually say NP 1 minus P are both at least 10. And if you think back to when we looked at binomial, that's meaning the mean and the variance are both at least 10. So the samples from each population must be taken at random, which is a common theme throughout hypothesis testing. When we write our hypothesis, our H0 is always going to be pi A equals pi B, which means that the population proportion of A is equal to the population proportion of B, and our H1 will be that pi A is less than pi B, or pi A is more than pi B if it's one-tailed, and pi A is not equal to pi B if it's two-tailed, meaning the population proportion of A is not equal to the population proportion of B. Now in our formula book we have these two formulas here which we need to combine together. So we can find P, which is the pooled proportion, by using this formula here, and then we are going to use that to help us to find what's called the standard error here, and we're going to have the difference between our population proportions there. And because we are treating this like it is a normal approximation, we're going to have to use inverse normal to get our critical value, and if the test statistic is smaller than the critical value, then we're going to accept H0, and if the test statistic is bigger than the critical value, then we are going to reject H0. And we need to make sure that in our conclusions we are talking about the proportions. So here in our example, we have Jamal is very interested in the proportion of Skittles that are green. He suspects that the manufacturers don't allocate the same proportion of green Skittles to small and huge bags. He found that in a small bag of Skittles, 13 out of 52 were green. So that is for our small bag. In the huge bag, only 23 out of the 186 Skittles were green. So that is telling us about the proportion for our huge bag. So then we're trying to investigate at a 5% significance level whether there is evidence for Jamal's suspicion. So all it's saying here is that he suspects that the manufacturers don't allocate them the same proportions. Okay, it's not saying that one of them is more than the other or less than the other. It's just saying that he thinks that they're not the same, which means that this is a two-tailed test. So our H0 is going to be pi S equals pi H, and our H1 is going to be pi S is not equal to pi H. And it's a good idea to write down what those symbols are meaning. Sorry, my H looks a bit like a 4 there. There we go. So pi S is the population proportion of green Skittles in a small bag. Pi H is the population proportion of green Skittles in a huge bag. So now we need to write down what our proportions actually are. So for this, we are using our information here in the questions. So we're going to have PS, which is our 13 out of 52. And we're going to have PH, which is going to be 23 out of 186. And here our N is 52, and our N for the huge bags is 186. So now we're ready to use our formulas. If I just scroll back up a little bit, we are going to have to use this formula here to pool our proportions together. So that means that we're going to have 13 out of 52 times 52 plus 23 out of 186 times 186, all divided by 52 plus 186. Now some people may be wondering why we are using this method here when it just cancels out to give us 13. Well, sometimes you won't be given this information as it was in this question, where it says that it's 13 out of the 52. You might just be told that 20% of Skittles in a small bag are green and 40% of Skittles in a huge bag are green. So you might not always be given how many it is out of the total that you then make into a probability. You may just be given the probability straight away. So it's a good idea to practice using the formulas so that they always work. So we're going to have 13 over 52 times 52 plus 23 out of 186 times 186 divided by 52 plus 186. So our pooled proportion is 18 over 119. So now we're actually going to use the formula to get our test statistic. So our test statistic is done by having a look at the difference between our proportions on the top divided by our standard error. Now if we have a quick look at the formula for the standard error, we can see it looks a lot like our SP squared formula from the 2 sample t-test. So we have P, which is our 18 over 119, times 1 minus 18 over 119, times 1 over n1 plus 1 over n2. So that's 1 over 52 plus 1 over 186. And then we can put this whole thing into our calculator at once. We don't need to work out the denominator separately if you don't want to. So we've got 13 out of 52 minus 23 over 186 divided by the square root of 18 over 119 times, in a bracket, 1 minus 18 over 119 times 1 over 52 plus 1 over 186. So our test statistic is coming out as 2.5 0.25 to 3 significant figures. And remember, it said in the instructions that we're going to have to use the inverse normal function. So dist, norm, inverse normal. We're going to have to use this part of our calculator to find our critical value. Now, the most important thing, first of all, is that it says variable, so we can type in what we need. And because even if we did end up with a negative value here, we can look at the magnitude of it and compare it always with the positive critical value. We're always going to make it so that our tail is going to the right, because that's always going to give us our positive critical value. Now, when we're looking at what the area is going to be, we have to remember that this is a two-tailed test, because it was that they were not going to be the same or they were going to be the same. So it's a two-tailed test, which means that usually if this was a normal, binomial or normal question, we would halve our significance level. And we're going to do the same thing here. So we're going to put 0.025 as our area. And because we're getting our critical value from the standard normal distribution, we want our standard deviation to be 1 and our mean to be 0. There we go. So our critical value from the calculator is 1.96. And as it said in the instructions above, as our test statistic is bigger than the critical value, that means that we are going to reject H0 at a 5% significance level. There is sufficient evidence to suggest the proportion, keyword there, proportion of green skittles is different or not the same in small and huge bags. So that's the end of part A. Part B, explain why your test is appropriate and whether the approximation is justified. So that means that we're having to look at this bit here to see if our NP and our NP1 minus P are at least 10 for both of these. Well, for the first part of that, for the small bag, remembering that our N is 52 and our P is 13 out of 52, our NP would be 52 times 13 out of 52, which just gives us 13, so that's okay. And our NP1 minus P would give us, I have to use my calculator for this, so that's doing 52 times 13 out of 52 times 1 minus, in a bracket, 13 out of 52. So 52 times 13 out of 52 times 1 minus 13 out of 52 gives us 9.75. So that is not good. Let's check if any of the other values end up giving us a value that's less than 10. So for our huge bags, our N was 180. 6. And our P was 23 out of 186. So our mean, our NP, would be 186 times 23 over 186, which just gives us 23. And our NP, 1 minus P, would give us 186 times 23 over 186 times 1 minus 23 over 186, which gives us 186 times 23 over 186 times 1 minus 23 over 186. Which gives us 20.2 to 3 significant figures there. Okay, so it's this value here, which is meaning that actually it wasn't appropriate for me to do the test. So as NP 1 minus P for small bags, and remember that's talking about the variance, is smaller than 10. This means using the approximation was not justified. So we've got a couple more parts to this. So part C, explain whether you could have made a type 1 or a type 2 error. So these last 3 parts of the questions are revising old material that we have already covered. So if we have a look here, we rejected H0. If we remember back to our errors, if H0 is true but we reject H0, that's a type 1 error. So for C, we could have made a type 1 error as we rejected H0 when H0 could have been true. And it's not saying to explain it in context at this point, so that's enough. Part D, rephrase your answer to part C in a form Jamal could understand, assuming he is not familiar with statistics. So this is where we're having to put it into context. So for part D, what this actually means is that we concluded that the proportion of green Skittles were not the same in small and huge bags. So that's what we concluded from our test, but we're saying we made an error. So when in reality They are the same. So that's not using any technical language, it's just explaining what we found in context, and then actually in reality what we found was different. The last part from this one, if we were to repeat the test for a different type of sweets, what change or changes would be necessary if we wanted to I reduce a type 1 error, I a type 2 error, and I both types of errors at once. So this is going back to thinking about when we looked at power. If I can just skip back to that and find out which page we were on. Okay, so this is the type 1 and type 2 errors. So here, the probability of making a type 1 error, if you know what the significance level is just alpha. So if we're wanting to reduce the probability of making a type 1 error, we can reduce the significance level. And here, remember that power is just 1 minus the probability of making a type 2 error. So if we're looking at ways that we can increase power, that's meaning we're looking at ways that we can decrease the probability of making a type 2 error. So if we increase the sample size, it's an easier way to increase the power. We could increase the significance level, but remember that that's going to have the opposite effect on the type 1 error. We could improve the process, which means that we could decrease the standard deviation. We could choose a larger value for the difference between the population means, or we could use a directional hypothesis test. So we could increase the sample size, which would decrease the chance of making a type 1 error, and we could make it a directional hypothesis test, which would increase the power, and it would also decrease the chance of making a type 1 error. So if I can go back to where we were answering the question. So ways that we could just, sorry about that. There we go. So ways that we could just decrease our probability of making a type 1 error. So this is for E, I. We can decrease a type 1 error by using a 1% significance level instead instead of 5%, but this is going to increase the chance of making a type 2 error, so it's not decreasing both of them. For part 2, we could increase our sample size to decrease the chance of making a type 2 error, and to decrease the chances of doing both of them, we could use a directional which means one-tailed hypothesis test. So those last 3 parts there were just a recap on some old material that we have already covered, but part A and B is covering how we can test for a difference between population proportions. Thank you very much for listening.